AB Calculus, Section 8.4, day number 1 on exponential models. As a class opener, your instructor would love it if you would fill out this chart here with derivatives, integrals. Pay attention to, here's your column of derivatives, here's your column of integrals, and then some composite function derivatives over here. I want to highlight two integrals. Ooh, that was crazy. These two here, tan and cotan. These both can be done using a u substitution. Okay, so I'll play with that one a little bit. But as it notes down here, these are difficult, and we don't believe you'll have to likely use those on an exam, but just to be aware, just in case. Okay, I'm not going to fill this chart out right now, but I'm sure there's a filled out, completed version of this somewhere online, and if there isn't, let us know and we'll get it to you. All right, let's go ahead and get into exponential models. Okay, so exponential models, we're gonna get into something that you've seen in pre-calc before and may not have known where this particular setup has come from, but we're gonna make some sense of it today in this lesson. So let's go ahead and read here real quick this introductory paragraph, and then we'll get down to it. So the rate of increase in population during a short period of time is directly proportional to the size of the population at the beginning of the period. This can be modeled with a differential equation. What is a differential equation? An equation which involves derivatives and whose solution is a function. So remember proportionality from pre-calculus. So we could say, for example, that area is proportional to the square of the radius, right, with a constant of variation of pi, right? That's direct proportionality. Recall that inverse proportionality, let's say y is inversely proportional to x, we could say that y equals k over x. So here is direct proportionality, here is an inverse proportionality. Okay, so keep that in mind as you work through the homework, and you might see problems that involve that kind of wording. Okay, so let's continue with this example. I know that the change in population is directly proportional to the population at the beginning of the period. So dp dt, the change in population is directly proportional, right? Directly proportional to the population at the beginning of the period. That's our setup for this differential equation. Okay, so let's separate our variables and integrate to find the solution to the differential equation. Okay, dp dt is equal to k times p. I split my variables, bringing p to the left side. 1 over p dp is equal to k times dt. Okay, my variables have been separated. Let's go ahead and integrate, and recall that k is just a constant, right? That's a constant of variation. So I would get the natural log of the absolute value of p is equal to kt plus c. Okay, now since population is always positive and non-zero, right, then we can really just refer to this as the natural log of p and don't have to worry about the absolute values. Now, there are cases where we do worry about the absolute value. We'll see that in the homework, and we can talk about that later. Okay, so the natural log of p is equal to kt plus c. Let's solve for p. Okay, so I'm going to take e to the power of both sides. The property of exponentials and logarithms tells us that e to the ln of p is just equal to p. And of course, the right side is e to the kt plus c. Now I'm going to use properties of exponents on the right side to write this as e to the c times e to the kt. Okay, so e to the c, what is that, right? Well, we can actually define e to the c as the initial population. So the current population, right, or the population at time t, is going to be equal to p sub 0, which would be the initial population, e to the kt. Now, how did I get that? Right, because look at that. Okay, yeah, great, you knew that. Well, how did I know that? Well, I took and I plugged t equals 0 in. If I do that, then p equals e to the c times e to the k times 0. k times 0 is 0. E to the 0 is, of course, 1, and therefore p is equal to e to the c. And, of course, p was our initial population. Okay, therefore, the population at any given time, here down in this like teal-looking blue coral, whatever you want to call that, the population at any given time is the population initially times e to the kt, where k is some constant of variation, and of course, well, constant in that sense, and t is the units of time since whenever the population was recorded. Okay, so let's continue with this idea of half-life. All right, so to work with half-life, what we do is we set p equal to half of the initial population, right? So here's our initial population. Half of that is whatever our population is at time t. Okay, so we're going to actually formulate a nice formula that can be used to find the amount of time it takes for, let's say, some kind of material to decay to half of what it was originally, or for a bank account to decay in its value, or whatever it might be. If you have a decay model, this formula will end up helping you to get to where you want to be quicker. Okay, so we start with p equals p sub 0 e to the kt. Now we know that the population, or the amount, is going to be half of what it started at. Okay, so our objective is to find the amount of time such that it would take that to happen. Okay, so if I divided out p sub 0 from both sides, I just know that I'd get half of e to the kt. Okay. Now, where do we go from here? Well, I'm going to take the natural log of both sides. Natural log of half is equal to the natural log of e to the kt. On the left side, I'm going to leave things alone. On the right side, I'm going to use a property of logarithms, which tells me that the natural log of e to the a is actually equal to a. Thus, this is equal to kt. Okay, so now I solve for t. T is equal to ln of a half over k. So if I know this constant k, depending on the scenario, right, I can take ln of 1/2 over k, and what this gives me is the amount of time t such that the half-life occurs, half remains. Right, so if this is population, in t years, half the population will remain. If this is some kind of, biological element, and that element is decaying, t would be the amount of time at which that element would decay to half of what it was originally. Now, if you want, let's say, t such that 3 times the original amount, right? It triples, or it is 5 times as large, or it is p times as large, right? All that you do is the time would be the ln of that value, 3, or whatever it might be, ln of p. P is a bad variable to use, but you get the point, right? Maybe I'll call that g as in growth, right? G times larger. Okay, you can use that formula to find the amount of time it would take for that to happen. Okay, the importance of this formula cannot be stressed enough. Okay, there will be questions that could take you a long time if you decide to go about it the wrong way. But if you know the value of k, and you know you're seeking half-life, this formula will make things go much quicker and more efficiently. Okay, just to reiterate, we end up getting this, right? This is an exponential model, and depending on k, will determine whether or not this is a growth or decay model. If this is a growth model, you won't ever be asked for the half-life. If this is the decay model, you'll never be asked for any sort of growth ratio, right? But if you're looking for half-life, and the amount of time it takes for half-life, t will equal ln of 1/2 over k, and this will be the time it takes for the population or otherwise to decrease by 1/2. This is an important topic. This is a very important formula as mentioned earlier, so make sure that you're privy to that. Let your teacher know if you got any questions, and we'll see you next time.